So we'll come back to that was just in terms of introducing the modes. Like I said, that's really, I probably should have started with that last time. That's like first day of a fracture mechanics class. So now what we want to look at is the a model for, like I said at the beginning, a model for doing predictive analysis of hydraulic fractures, a simple model. And we're going to start with looking at, because in a geomechanics application or a hydraulic fracture application, we have a crack essentially that is embedded in a essentially infinite media with far field stresses, right? So we have these far field stresses, and well, in general, you could have, so if this is X, Y, Z, in general, you could have even shear stresses in the far field. And then we have stresses on the crack face as well. I'll define those in a second. So, but let's call the stresses in the far field. And so the equations we're going to show will be general. We of course know our far field stresses are the tectonic stresses, the SH min, SH max, SV. But the equations are more general than that, in the sense that they're for a complete stress tensor, whereas we'd have the simplified case. So I'm going to use the little r for remote, far field stresses. So we have the fully populated stress tensor. It's symmetric there. So those are the remote stresses. And then if we sort of zoom in on the fracture, this little notch here is just meant to indicate that the fracture is sort of, in this model, infinite into the plane. Then we're going to have, in this coordinate system of the fracture, we'll also have a tensor, which are the stresses on the crack faces. So there we're using the superscript C. Now, if the stresses on the cracked faces are from a hydraulic fluid, can a hydraulic fluid impose a shear stress on a solid surface? No, right? So it's really just the only ones we care about are the pressure, right? The diagonal terms. But we're going to define, for now in the general case, we'll define what we call the driving stresses. So these are the things that are going to drive mode 1, mode 2, or mode 3 crack extension, as defined earlier. Right? So since mode 1 is a pure opening mode, we're going to call the driving stress delta sigma 1. So this is the stress that will drive an opening mode fracture. And so in these terms, it's the YY component of the remote stress minus the YY component of the stress in the crack. So it's the stress difference between what's on the crack face and what's remote, holding it closed, right? So Mode 2 is a shear fracture, right? Shear sliding mode. And mode 3 is a tearing mode. Okay. So these are the crack driving stresses. So now we're going to follow some analysis that's in a paper by a guy named Pollard and others, 1987. I put that there just in case you want to see all the details, because we're not going to show all the details. But they use a so-called tripolar coordinate system. And what that looks like is so it's centered on the crack of length 2A, where if we're interested in any point, let's see. So this is the point A0. Likewise, there's a point over here, minus A0. And then we define this coordinate system. So we basically have three vectors that all point at a common point. And the vector that emanates from the point A0 is characterized by the radius R1 and the angle theta 1. This is the origin. So it's characterized by R and theta, and from minus A, talking about theta to R2 characterizes it. And then it just, when you work, we're not going to show all the details of the derivation. That would take 2 class periods. But when you work through all the details, it turns out you get some common terms in the solutions that show up a lot. And so we're going to kind of define some convenience variables, because these terms show up over and over in the solution. I don't know why I keep wanting to make that stress. It's theta. Okay. All right, so in this coordinate system, they derive the displacement field for any point in the body, according to these coordinates. So around a crack of 2A, at any point, this is the displacement field. That I'm about to write it down. So U, the displacement in the x direction, so this is x. The displacement in the x direction is equal to 1 over 2 mu, where mu is the shear modulus. The crack driving stress, the mode 2 crack driving stress. Hmm. I'll post the notes. I'll just keep moving forward. Sorry. What? No. We'll talk about that. No. Yeah, another advantage of this thing over my other one that is I can easily make a PDF of the notes. So I don't know if you saw, if you looked on the course webpage, I actually posted a PDF of the actual notes that I derived last time. So I'll do the same today. I guess I should have told you that before you broke your hand. Okay, so on a cracked surface, all right, on the cracked surface, this is the case where sort of all of these angles collapse, right? And so I drew them really small, but we're sort of looking at in the limit of these angles collapsing, but they can collapse in both. They can collapse in this way, you know. So this is 0, 0. This is A 0. This is minus A 0, right? So they can collapse in both directions, right? And that would both be valid on the cracked surface. So on the cracked surface, we have R is the absolute value of X. Remember, X is this guy. And since it can go either way, R is the absolute value of X. R1 is A minus X. R2 is A plus X. Theta is either 0 or pi. Theta 1 is minus pi or pi. Theta 2 is 0 or 2 pi. And then our convenience variables, R is this, and gamma is either pi over 2 or 3 pi over 2. So if you plug these values in to those equations, and now because some of these have two values, right? You have to plug them into the equations for each pair for twice. You know, the first set of values and the second set of values. And if you do that, then what you'll get is a set of equations that looks like this. And the plus or minus now refers to y equals 0 plus y equals 0 minus. Okay, so this refers to the scenario where, actually, this is a little bit, I drew this a little bit wrong. The idea is that we can collapse to the cracked surface in either way, right? So if we're sort of taking the limit as all those angles approach from this side, approach 0 from this side, or take the limit as all those angles approach 0 from the other side, right? And that gives you the plus or the minus, okay? And so then we can define a jump in displacement at the crack tip for I equals x, y, z, and m equals 1, 2, 3. So there's a discontinuity at the crack tip, and that jump discontinuity is the plus values minus the minus values, right? And so then what that is, in mode 1, mode 2, mode 3, is that. So that defines the mode 1, mode 2, and mode 3 displacement discontinuities associated with these driving forces, okay? And at least in the mode 2 case, this is something that's pretty observable, right? If we go to the field and you have a crack, and there was, say, originally some indication of a natural fracture or a line segment or something like that, and then you were to put it into shear failure, and the crack extends such that now that line looks like this, right? Something that was perfectly lined up, whether it was a natural fracture or whatever. Well, now it's not lined up anymore. Well, this right there is the mode 2 displacement discontinuity. Right? And x is your distance from the origin to the tip of the crack, which you see becomes singular. It's like that square root singularity as it gets close to the crack. So these displacement discontinuities are accurate in the limit of a limit of this approaching the crack tip. So I guess, in other words, what I'm saying is it's going to be 0 when you evaluate it it's going to be 0 when you evaluate it right at the crack tip. There's no discontinuity there. But if you move off the crack just a little bit, then that's your displacement discontinuity, which the mode 1 displacement discontinuity is an indication of the width of the fracture. Right? So if you know the width of the fracture, then you can solve an equation for Reynolds lubrication theory equation. This comes from the solution of the Navier-Stokes equations between two parallel fixed plates, right, in the presence of a pressure gradient. So if you know the width, you can solve for the pressure gradient along the fracture wall, right? And if you know the pressure gradient along the fracture wall, these contribute to your driving stresses. I mean, the pressure gradient is the stress on the pressure is the stress on the crack face, right? And then your far field stresses define your crack driving stress. Then you can solve for the displacement discontinuity. So they're coupled, right? So you have to solve essentially these two sets of equations in a coupled way. And then if we go to the solution, let's see, from Jim Rice, 1969. Jim Rice is easily he's easily the most famous guy in fracture mechanics. He's still active. He's a professor at Harvard. He's quite old now, but easily the most famous guy in fracture mechanics. So if we go to one of his solutions, one of his many contributions to the field, what we can get from the displacement discontinuity is a measure of the stress intensity factor. So the stress intensity factor the mode 1 stress intensity factor is this. The mode 2 stress intensity factor is this. So if we have a measure, this is actually what I was meaning to say earlier with respect to the square root singularity. You see, so R is the distance from the crack tip. And so as that goes to 0, this thing blows up. But if you're a small distance away, it's very accurate. Right? So if you know the displacement discontinuity, a small distance away from the crack tip, we can get an estimate of K1 and K2. And then we can decide if the crack's going to propagate. So if K1 exceeds K1C, which is a material property we can measure in the lab, the crack will grow. If K2 exceeds K2C, which is a material property we can measure in the lab, the crack will grow. Right? So we can solve the coupled equations for fluid pressure and width for the displacement discontinuity, and then we evaluate the stress intensity factor from the displacement discontinuity, and then we can decide if the crack will grow. And so the way this is done computationally is, our crack is divided up into line segments. Discrete. Anything in a computer has to be, you take something continuous and you make it discrete, right? So we take our crack and we break it up into individual pieces. And usually these are the displacements would be evaluated at the midpoints of these line segments. So your displacement discontinuity. So your displacement discontinuity, this distance r would be 1/2 the element size from the actual crack tip. Right. So this would be r, and it this becomes more accurate as r goes to 0. So as your element size gets smaller, right? You're going to approach the crack tip, but you'll never get right to it. If I take these elements and I divide them by 2, 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 I'm going to approach the crack tip, but I'll never get there. Right? And so what we do, or what they do in these types of software, is then they'll add an element. So if this is true, they'll add an element to the end. Okay? But in a mixed mode fracture, how do you know where to add it? Does the cracks always grow in a perfectly straight line? Right? So you know that you need to add an element, but where do you add it perfectly straight or at an angle to where it was? So that sort of takes us to our next how to add it is based on something called max